Everyone, I'm Rhema from the Department of Robotics and Automation. Now we're gonna see the two different ways of control flow in an autonomous drone. The first one is control signal path. Here, the signals from the transmitter it reaches the receiver. Once it reaches the receiver, it is just forwarded. It's forwarded to the flight controls, that is FCs, just in order to decide their moments, decide their like where should they go. They should go up or they should go down or something. Some like movement of the drones are controlled by flight controllers. They control the movement of the drones. And then we have a motor output flow. Here, once the signals reaches the FCs, that is flight controllers, the signals are then passed through the ESCs, which is electronic speed controllers. This electronic speed controllers controls the speed of the motors that we have used in this drone. They control the speed of each motors so that drone can move stably without falling down and some occurring some errors in that. And yeah, first now we can see the process of it. Okay, so first of all, the transmitter. The transmitter sends the signals. I mean, from any sources such as remote, and then the signals are passed from the transmitter, and it flows through the air, and it reaches the receiver. Once the signals reaches the receiver, it is passed through the FCs, that is flight controllers, which acts as a brain for the drone. And then so now the flight controllers will decide how a drone should react for each time. And then from the flight controllers, the signals are passed to the ESCs, that is electronic speed controllers. So now
So I'm Joana and I'll be explaining you guys the methodology of our project. So first step is design and planning. In this step, we decide the frame size, motor, and battery based on what the drone needs to carry. We also choose a suitable flight controller and ESCs. Second step is hardware assembly. Here we assemble the physical parts. Motors and flight controllers are mounted, ESCs are connected, and the receiver is attached. Third step is software setup. We install firmware like Flight or INAV. In our project, we use Flight. Then we calibrate sensors and set up the radio channels. Fourth step is testing and calibration. We test arming, disarming, and motor rotation. We tune the PID controller to make the drone stable. Fifth step is flight testing. We do the first flight testing in an open area. We check stability, adjust PID if needed, and review flight logs.
I'm Jivinta and I'll be telling about the hardware we used in our drone. The drone is built on a carbon fiber frame, measuring 17 cm by 4 cm, which keeps it lightweight yet strong. We use three main electronic boards. First is the power distribution board or PDB, which connects to the battery and supplies power to all components. Next is the flight controller, the brain of the drone, responsible for stability and movement. Between them is the electronic speed controller or ASC, which regulates the voltage and controls motor speed. To keep the design compact and well balanced, we used a 4-in-1 ASC instead of four separate ASCs. This reduced the weight, improved wiring, and made the drone more efficient.
So this is the conclusion of our project. This autonomous robot project shows the complete journey from designing and assembling the robot to setting up the software and finally testing it in the field. By combining the right hardware, stable firmware and custom Python features, we were able to achieve smooth, efficient and fully controllable as an autonomous flight. Overall, this project proves how practically and reliably drone technology can be engineering and programming work together effectively. And thank you.